Hey class, one more video here on kind of solving the problem we started in class where there's a door and people are throwing mud at the door. I don't know why. And the mud is sticking to the door afterwards. And so the door hinge is down here. This door is 5 kilograms and has a radius or width of 0.5 meters. And we have one mud ball coming in here, 1 kilogram mud ball hitting at a right angle, going 8 meters per second. And it hits a little lower on the door at 0.34 meters. And this one here is coming at this angle, kind of a steeper angle. It's going faster. It's also 1 kilogram, but it's going 11 meters per second. And it's hitting right there at an angle from 40 degrees from horizontal there. But it hits at the very end of the door. So we want to know what's going to happen to this door afterwards. We're going to assume that initially it's at rest, so the initial angular acceleration is 0. Yeah, so this is a conservation of angular momentum problem. We're going to have a before and after. So this is kind of our before, right? While the mud is flying through the air and the door is stationary. And our after looks like this. We have the door now the mud is stuck to it. This clump of mud is, I guess, clump of mud on the left is down here. And the clump of mud on the right is up here. But now that it's struck, the door is going to be moving one way or the other. Oh, sorry, I wrote acceleration here. I'm very sorry. I meant to write the initial rotational velocity. So after that, we're going to be rotating one way or the other. We don't know which yet, but we want to find the rotational velocity after we hit. So, right, we're going to be doing conservation of angular momentum, the angular momentum of the total system before equals the angular momentum of the total system afterwards. All right, and what's our equation for the angular momentum, right? We want the, for each object, we would calculate the angular momentum of each object and add them up to find the total angular momentum of the system. Right, so we want the angular momentum for before. You can have 3 different angular momentums to think about, right? The angular momentum of the door and the angular momentum of the 2 different mud balls. So we'll do that mud ball 1 and mud ball 2. And afterwards, it's all kind of one system, right? And we're going to think about the angular momentum of this thing afterwards. So angular momentum is moment of inertia, right, times the rotational velocity. But maybe our moment of inertia of the door has changed, right, because we kind of added point masses to it. So we'll have to think about that in just a minute. But let's go back and think about the before case. Okay, so the initial angular momentum of the door. And the angular momentum of the door is going to be the moment of inertia of the door times the initial rotational velocity of the door, which is 0. The door has no angular momentum initially, 0. But that doesn't mean our system doesn't have angular momentum, because we have to include the mud balls in our system. So what do? Right? We need to think about, in this case, we're converting the linear momentum of our mud balls into angular momentum. And if you remember, angular momentum is the cross product of the linear momentum and the radial vector towards between, where it's hitting and the rotation point. So it's going to be the linear momentum times the radius times sine of the angle between them. Right? That's the cross product solution. So we need to do that for each of these guys. And also, right, angular momentum is a vector, so we need to think about the direction. One's going to cause clockwise rotation, one's going to cause counterclockwise rotation. So we need to decide which is which and give the appropriate sign. So this one coming in from the left, it's going to hit the door and it's going to cause that to rotate clockwise, right? So we'll call clockwise positive. So mud ball 1 should be positive angular momentum, and mud ball 2 should be negative angular momentum. So fighting against each other through the door. Okay. Right. So the linear momentum of mud ball 1 is just going to be its mass times its velocity. And then we would say it's hitting, the radius is where it's hitting. That's this term here. That should be 0.34 meters. And sine of the angle. So that's the angle between the velocity vector and the radius vector. So the velocity vector is coming in horizontally and the radius vector is going down vertically. So it's 90 degrees. Sine of 90 degrees is 1. So for mud ball 1, our angular momentum will be the mass of mud ball 1, which is 1 kilogram, times the velocity, which we said was 8 meters per second, and then times the radius, which we said was 0.34 meters. And now on to mud ball 2. So we said mud ball 2, that's going to cause counterclockwise rotation, so it should be negative for sure. So whatever it is, it's going to be negative. And it's going to be the linear momentum of mud ball 2. It's mass times velocity. So 1 kilogram times, it's coming in on 11 meters per second. And where it hits, it's going to be the radius. This comes in at the very end, 0.5 meters. And the last thing is the sine of the angle between them. And this time, we're not coming in at 90-degree angle. So let's think about this for a minute. Okay, if we're coming in here and we're hitting just like the other person at a perpendicular, our angle would be 90 degrees, right? And if we would throw like this, parallel to the door, that wouldn't make the door rotate at all, right? If you threw straight down, that wouldn't make the door rotate. So actually, we're 40 degrees from 90 degrees, actually, because this direction would be 90 degrees if we're through horizontal, and we're 40 degrees less than that. So our angle between the velocity and the radius vector is actually going to be 50 degrees. So 50 degrees. Okay, so to finish things up, we had calculated the angular momentum of the door initially, which was 0, and of each of the mud balls. One coming in from the right was positive. This one was negative. We added all those things together. I get that the total angular momentum before the mud balls hit is going to be negative 1.5. Okay, cool. So remembering that the total angular momentum of the system, this is our total angular momentum of the system before the hit. that's going to be equal to the total angular momentum of the system after they hit, which is going to be the moment of inertia after times the rotational velocity after. So what's the moment of inertia? If we know the moment of inertia of this thing after the mud balls stick to the door, we can solve this answer, because then W prime, the only thing we don't know. So when we're calculating the moment of inertia of our systems, we just add them together. So we have a door and two mud balls, which we're treating as point masses. So the moment of inertia of the door is going to be 1/3 mass of the door times the radius of the door squared. And the moment of inertia of a point mass is just mass times radius squared. So for mud ball 1, it would be 1 kilogram times 0.34 squared. And mud ball 2 would be 1 kilogram times 0.5 squared, because they're at different radii. Right? So we just add all those moment of inertias together. And I get that the total moment of inertia of this system is 0.78. Therefore, we have this equation. Negative 1.5 equals moment of inertia times our new rotational velocity. We just flip it around to solve for the rotational velocity. I get that our rotational velocity after we throw the mud balls at the door is negative 1.2 radians per second. Maybe I made a mistake, maybe I made a typo, but hopefully, even if I did, this is a useful video to illustrate how we walk through the problem. All right, sorry for getting these videos to you so late, but hey, I stuck around till 6:30 to get you these videos. So good luck tomorrow. I'll see you soon.